Welcome everyone to our Physics Friday Colloquium. We have two students, master students presenting today. We have also one next Friday with three students presenting. So it's my pleasure to welcome you the first student, Meek Patel. He worked at CERN and he worked with Dr. Gao. His title of the presentation is there, and without further ado, let's welcome him.
Thank you so much everyone for coming today. My name is Kumar and I'm a graduate student here in the physics department. Today I'm going to talk about the hunting for a new Higgs boson with the Atlas at CERN's LHC. So my main focus today is on the validation background method for the beyond the standard model, a new channel for the Higgs SH to BB tau tau. Before I begin, in this talk, I'm going to cover why search for the new Higgs boson beyond the standard model, and what does to X to SH and BB tau tau final state look like. Then I will tell you why we need the background estimation and what is the bigger major problem that we are looking into, and how I use the data-driven fig factor method to evaluate this evaluate the fig factor in the final state, and at the end we will look into it some of the results which I got from the 2022 Atlas data, which is based on the run 2. So in single line take home message, so this work validate whether an established HH to BB tau tau fig factor method can be reliable applied to the new SH search topology. So all we know, the standard model described the fundamental particles and the interaction, and after the discovery of Higgs in LHC in 2012, it is well recognized. However, it is not complete because it not describe the dark matter, which is about 27% of the universe energy density, neutrino mass, and the hierarchy problem, which is why Higgs mass is so light. So based on that, the standard model predict only one physical Higgs boson in the decay channel, and the many BSM, which is beyond the standard model, predict additional scalar particle, which is the main thing in this talk. And some of the examples are like two Higgs double model, supersymmetry, single extension. An additional Higgs boson could help address open questions such as dark matter, CP evaluation, and the hierarchy problem. So as you can see here, my search channel in this study is X goes to SH. S is the scalar particle, and H, which is well known Higgs boson, and then the final state is BB tau tau. So here H is 125 GeV. For the study, I take the higher masses value in order to examine that if we use the analysis tool and run the higher masses for like 1000 for X and take example for S as a 550 and then rerun, does the already established framework which take around 3 years at the Atlas to build the framework for HH to BB tau tau, and here I tweak that framework and convert it into for SH to BB tau tau. The final state which we are looking into it's a two B-tagged jets from the S to BB and two hadronic tau candidate from the known Higgs to tau tau. Missing transfer momentum or PT from the neutrinos in tau decay, and reconstructed mass variable to search for the resonance. So mainly we are looking for exactly two B-tagged jets and two hadronic tau candidates. So for that we need to get a data in order to process all those background and estimate the fig factors. For the data, we are solely rely on the a Large Hadron Collider, which is world's largest and most powerful particle accelerator. It's in the Geneva. It's underneath around 100 meters down to the Geneva, and the total length of the LHC is 27 kilometers. Currently, run-free collision energy is 13.6 TeV. So particle start from here, and then we strip the. So we take the hydrogen, and then with the ionization we strip protons, and then we accelerate that proton into the boosters, so that after the multiple time boosting, they reach the speed of approximately the speed of light, and two proton bunches go, one in this direction and one in this direction, and then we collide into four main LHC experiment, which is CMS, Atlas, ALICE, and LHCb. Mainly, I rely on the data for the Atlas detector. So here you can see this is the Atlas detector, which is 46 meter long, 20 feet meter high and the wide, and 7,000 tons the detector mass, and it's also 100 meter underground. This detector has a multiple layer. So the inner detector, it tracks the charged particle. Then the calorimeter, it measures the particle energy, and then the outer detector, it identifies muon, jets, and taus. So we collide two protons, and we get bunch of particles. But some particles behave differently, and we get a fake particle. It's something like that. You order something online, and initially when you order, you think it's a real product, and it turned out when it get delivered, it turned out it's totally fake. So we are looking the same situation here. So the proton showering is something like the jet hadrons, and we are also looking for taus, which is hadronical decay, because 65% time all the taus decays hadronically, and they are, as you can see here, they are mimicking the same kind of jets and same kind of tau candidates. So we need to identify and remove those QCD jets, which is mimicking exactly like a T candidate. So the reconstructed as it's a one prong and three prong. One prong and three prongs are shown here. So for example, this is a 0, and this is pi negative and pi positive. So this is called one prong. And if it is three prong, then you are looking for 3 pi and 3 negative. It goes further like 5 pi's, but rarely we see such kind of data. Now the signal versus background. So this is just an illustration to show you that the standard model process that can be produced similar detector signature. So signal is expected to be very small, and background are much larger. So the blue line is the background, and the red one is the possible signal. So what we do, before we run the data, we do the Monte Carlo simulation and get the possible signal and the background, and then we compare with the observed data, and then look for that access for accurate background with prediction. We looking into the access, observed data, and the possible signal. So fake tau hadronical background. So why the data-driven estimation is important? So real tau background, which is Z to tau tau or T to T bar and dye boson, they are estimated with the Monte Carlo simulation, and the fake one, which ordinary jet misidentified as the tau hat candidate, which are multi-jet or QCD production, is dominated, like 65% of them are fake taus. So for that, we need to use simulation. We need to use the data-driven estimation. So the main challenge is fake tau background. Jets can look like the hadronic tau candidates in the Atlas, And what strategy we use? The fig factor method, a data-driven transfer from anti-tau hadronic events to identify tau hadronic events. So we can divide that fig factor into four sections. So 2 are the 2 charges category, and then 2 are tau ID categories. So first, the opposite sign. If it is opposite sign, they are the real, and if it is the same sign, then they are the fake backgrounds. And the ID is an anti-ID. So ID is something we define some sort of rules and then run the data. If the data is passed from that some sort of rule, we call it ID. And then again we run through the anti-ID, it's like losing the filter. So we allow some of the data which is not passing through the ID, but we allow into anti-ID, and then rerun again to the ID in order to get the clear data. So this is the standard fig factor method definition which I use. This definition I get it from the already established Higgs HH2BB tau tau atlas group. So we derive in the same sign, and then fig, which is fig enriched data control region, and then real tau contributes are subtracted using Monte Carlo simulation, and fig factor provide a data-driven transfer factor from anti-tau to ID events, anti-ID to ID events, and measured as a function of tau hadronic as a transfer momentum or pseudo rapidity and the prong multiplicity. So the SS fig enriched data derived fig factor, and then we apply for the opposite sign anti-ID events, and then look for signal like kinematics, and then we again apply for the fig factor weights event by event, and predict the fake tau hadronic background in opposite ID signal region. So this is the comparison between the already established HH framework and this is the SH framework. Here you can see the H goes to H, and here X, which is heavy particle, goes to the S scalar particle, and H the known Higgs particle. And we want 2 B jets and 2 tau hadronic. So in the HH to BB tau tau, and we have the X to SH, and then S to BB and H to tau tau, which is the similar kinematics and the signal. So we adapt the HH framework as a natural starting point, and then tweak that framework in order to run the SH particles. So this is the same visible final state BB to tau tau and similar background source. Same general fig factor strategy. What is the different? The different is the new heavy resonance X and the different scale mass for MS. So for this research, I gave the resonance X as a 1000 and the different scalar mass MS as a 550, and modify kinematic selection and the higher reconstructed mass range, which is around 2000 GeV. So the analysis workflow goes like that. So we adapt the Hadron framework, and then we process the run-3 data and the Monte Carlo samples, and we do lots of editing in the Hadron event selection and categorization framework, and then do signal and background histograms and combine the yield table, and comparing that yield table with the fig factor method, and then data prediction validation plot, and then fig factor method validation. For that data set, these are the benchmark points. So collision energy was 13.6 TeV, run 3 proton-proton collision, and integrated luminosity is 51.8 inverse femtobar, which is at last 2022 data. And as I told you, the benchmark point is 1550 GeV. So before we get into the results, what we did, we run the data and we try to check does this framework is really works or not. So we compare the data with the HH framework. So here in this plot and this plot, this is the OS region, so opposite sign, and this is the same sign region. So same sign region means the fake taus, and the opposite sign region means the real taus. So by looking at this one, here the black dots are the real data, and the stacks are the background. So as you can see, the jet tau hat fake, which is the totally blue, is the dominant background here, and the data and background ratio is also near to 0, which says that this framework is perfectly determining the backgrounds. After that, we get the 2 tag opposite sign because our final state was 2b and 2 taus. So 2 tag means 2b jets. So 2b jets, what we get, the 55% of multi-jet fakes, 23% of tau fakes, 9% of tau real, and the 6% tau leptons, and the other remaining Z plus and dibosons, etc. 7%. The predicted events was 25,160 plus and minus 64 statistical uncertainty. And what we observed from the data is 26,260 events, which is pretty good because the difference is 4.3% relative to the prediction. And the signal yield at this mass point is 7 events, which is negligible compared to the background. And this is the final result on that. So as here you can see, this is the reconstructed di-tau mass plot. Here the signal is peaking at 550, which is our S signal. We take as an assumption that if we take X 1000 and then X goes to the S and H, so S become 550, so we are getting the signal here at 550. And the background modeling is also pretty good because of the data and the background ratios is also perfectly fit. Here, this is the reconstructed MSH, that X was peaking at 1000, the signal is also peaking there. Here we can see a little bit difference between the data and the background, which I tried to remove that, but I was not able to. Then I reached out to the Atlas committee and they telling me the same, and their HH to BB tau data have the same similar uncertainty here at picking about 300. So the conclusion, the physics motivation, the extended Higgs sector are well motivated by the BSM theory, and X to SH and BB tau is promising search channel. The main channel was to fake tau's background from the jet. So this work validated the data-driven fake factor method for SH specific selection in the head-head channel. So we used the 51.8 inverse femtopers of run 3 data set at 13.6 TeV luminosity, and the demonstrated good agreement between data and background prediction, and results support the applicability of the HH derived fake factor for the SH topology. So this work contributes to the development of the Atlas search for X to SH, BB tau, and provide the validate fake tau background estimation for future signal extraction with the larger run 3 data set. This work is one of the first in Atlas for X to SH and SH to BB tau. This work is already presented in APS Far West section meeting in 2025 and Atlas Higgs working group meeting, which is H to BB tau 2026. I want a special thanks to the advising, mentoring, and the committee support, Dr. Yang Gao, Dr. Jason Beach, Dr. Douglas Singleton, Cesar Ali, Dr. Katie Green, and Gerardo Munoz, and institutional support by our Department of Physics and the Atlas collaboration. And thank you so much for listening.
Questions?
Could you go back to page 9? So in each tau decay, you'll miss at least one neutrino, right? And then also possible additional neutrinos from B, each B. So what's the range of how narrow is the peak you expect? The range of the peak you expect in this spectrum?
Okay, so the possible signal are sometimes really small.
Mm-hmm.
Even the my plots also showing. Let me show you here. So here, initially the signal was not popping up, the real signal, but then I did the multiply by 1000 in order to get the signal. So if you are looking at how much is going to be the difference, at the first glance I see the 0. But then when we multiply with the 1000 or 500, then we get a little signal, and then we can tell that this is the signal and the real data.
So the red curve on the right-hand side, that's what you expect from your simulation?
Right.
Okay, so it's like 100 GeV signal.
Right.
Something.
Right.
Okay, I see. Okay. Thank you.
So if you go back to the Feynman diagrams, like if you have SH, yeah, so right there. So the bottom one, so the S, can that all, so I mean, could you switch the topology so that basically S goes to tau plus tau minus and H goes to BB bar? And,
Yeah, so
and you distinguish between those, or they're the same?
no, we can do that. And even one of the student, Avi, he was also working on that. But his research is different. But we can switch that. But it takes, for this framework, we can switch that. We can get the results. But I never tested. I test with a different mass point. So initially I start with the X1000 and S170. Then I change the mass point with the X550 and S200. And then I test for the higher masses, which is X1000 and S550. And it worked pretty well in all those mass points. So I believe that if we change it, we can get the results.
So your S was, you actually tried 550 GeV, right?
Right.
So then you could also, in principle, so the Higgs is 125, 126, so it won't decay into TT bar, but the S, if it's 550, could decay into TT bar, right?
Right.
So, I mean, did you look at that? And actually, that seems, that would be the predominant one, because basically, I mean, well, anyway, the standard Higgs couples to mass, so the larger the mass, right, so
yeah, tau is the dominant background.
right.
And tau decays to the 65% decays to the hadronic channels.
Right. But the S, could it decay to TT bar? I mean, it seems like it could.
Yeah, it could. Yeah.
Questions? Now let's thank our speaker again. Our next speaker is Daniel Cooper. Dr. Doug Singleton.
And also Mike Bishop.
Mike Bishop. From Mass. Oh, he's not here. And the title is Novel Approaches to Generalized Uncertainty Principles and Related Results. Daniel?
So like we said, I'll be presenting on novel approaches, generalized uncertainty principles and related results. All the work here was used as part of my master's thesis, and I've been working with Dr. Singleton as well as Dr. Michael Bishop from the math department. So generalized uncertainty. So generalized uncertainty principles are a phenomenological approach to quantum gravity, where we seek to find some sort of minimal localization. They're not intended to be an entirely new theory of quantum gravity. They're intended to look for certain key features of quantum gravity that we expect to find, and then use that to guide future quantum gravity research. The way this is done is by, in some sense or another, modifying the traditional Heisenberg uncertainty principle that can be either deforming the shape of the Heisenberg uncertainty principle or leaving the shape alone, but providing some sort of cutoff where it doesn't go beyond that. This is achieved by modifying the position and momentum operators, where the canonical momentum, or position and momentum operators x and p, we construct functions out of those to come to our modified position and modified momentum operators. And then in the low energy limit, where the momentum is low, our modified momentum should become equal to our typical momentum, and our modified position should become equal, or approximately equal to our typical position operator. A really common choice that's been used in the literature for about 30 years is to start with this modified commutator here, and then construct modified operators, capital X and capital P, from there. And this is chosen because this particular modified commutator implies a minimal localization, delta x equal to h bar root beta, where beta is just a free parameter in the model that's to be experimentally determined. So a quick visualization of that. This orange line is the typical Heisenberg uncertainty principle, and everything below that is what is typically forbidden by standard quantum mechanics. This green line is our now modified generalized uncertainty principle, and the region in red is what is forbidden by this particular form of the generalized uncertainty principle. And then this green is what is allowed by this generalized uncertainty principle. So I'll be covering three main topics based on three different papers we published. Symmetrizing the operators, that's a very standard approach, or very common approach of picking that particular form of the commutator. There's a particular set of modified operators that have been of a lot of interest for about 30 years. However, that choice comes with a lot of underlying mathematical issues that present a lot of problems for performing calculations, as well as modify quantum mechanics in ways we don't really desire, and leads to a lot of just undesirable results. We managed to come up with a novel framework that seems to address a lot of the underlying issues in that framework. Next, I'll be going over a modified quantum harmonic oscillator. We took the standard quantum harmonic oscillator, put in our modified operators, and then looked at some of the phenomenology that came out of that, and tried to devise a way that experimentalists could try to place some sort of bounds on this gut parameter and this minimal localization to help guide future quantum gravity research. And then in the third paper, we demonstrated the compatibility of gut models with Lorentz invariance, which demonstrates that a minimal localization within fields doesn't explicitly imply or explicitly require that the physical structure of space-time itself is discretized. So starting with that symmetrizing of operators paper, the kind of standard set of modified operators that have been of a lot of interest for 30 years are for one, leave the momentum operator unmodified, and modify the position operator as this, so that when the momentum is very low, this becomes approximately equal to the standard position operator. But at high momentum, this beta p squared term will start to have some effect. Again, beta we expect to be incredibly small, as we haven't seen deviations from the traditional operators yet. This leads to this generalized uncertainty principle here, which implies a minimal localization of H bar root beta. This particular choice of modified operators means that this position operator is not Hermitian under the standard product. A consequence of this is that if you take the expectation value of the position, it can be complex valued, which is obviously a problem because position isn't observable, and so it should only return real values. The particular fix that KMM chose to address this was to redefine the measure under the inner product, so that the inner product now becomes this, and the measure is 1 over 1 plus beta p squared, rather than just 1. This does serve to make this modified operator Hermitian, but it comes with some undesired consequences that we'll go into a little more detail in a moment. The two main things are that the Fourier transform is no longer unitary, so it's not providing a unitary map from momentum space onto position space, as we are starting off in momentum space, and this means we can't come up with a typical position space representation of our states, and we can only get a quasi-position space. So our proposal is to instead take the one they proposed and take the average of that with its adjoint and use that whole thing as the modified operator. Doing that and then playing around with the commutator between little x and little p, to simplify it, we can arrive at this modified operator here, where we can see at low momentum these terms will go away, and we're left with the standard position operator, of course. But at higher momentum, we have this symmetric operator here. This leads to a number of advantages. It's automatically Hermitian under the standard inner product. Because we haven't modified the measure, the inner product is preserved, and our standard momentum space is also preserved. This doesn't modify the underlying structure of the Hilbert space. In quantum mechanics is much more similar to standard quantum mechanics, whereas theirs leads to a lot of more fundamental changes. Because of all of that, the Fourier transform still maps the momentum space unitarily onto the position space, and so we don't need a quasi-position space. We can get a typical position space representation of our wave functions. And we also found that this approach is inherently perturbative. The old approach, like I said, fundamentally changes the underlying structure. This one, the Hilbert space is unmodified, and any sort of states that come out of it are just a perturbation on standard quantum mechanics, which means we have a lot more tools in our tool belt to solve problems within this framework. So looking at the uncertainty relationship, this particular symmetrized operator that we chose, it leads to the same commutator, the same uncertainty principle, and the same minimal localization that KMM took up. However, the mathematical structure differs. So all the core features we were looking for, all the phenomenology that we want to look for in quantum gravity remains identical. There's no changes to it, but the mathematical structure is incredibly different. When we take that modified operator and look for the position eigen states, we get this big equation here, which is not much interest, being that it's kind of messy, but we can extract a lot of useful information out of it. Of course, C is the modified position variable, and it can take on any real number. These states, even though they're messy, they do span momentum space, and they are square integrable. If we take pairs of states, they're not orthogonal in general. However, if we make some sort of discretized lattice by setting C sub n equal to this here, where n is an integer, and epsilon is any number from -1 to 1, epsilon is just sort of a shifting parameter that allows you to decide where your grid is placed. And if we do that discretization, if we make that lattice, those states are orthogonal now. And so these psi sub c sub n form a complete orthonormal basis, and they are square integrable. If we take those position eigenstates and we do the Fourier transform from momentum space to position space, we can then get the standard position space wave functions of those states. And we weren't able to come up with a closed form for them. However, if we approximate them to first order in beta, we get that they are approximately k naught of x minus c over h bar root beta, where this k naught is a modified Bessel function of the second kind, order 0. And to contrast this to KMM, we were able to come up with a solution for these eigenstates, whereas KMM, because they have a quasi-position space, there is no standard position space representation for the position eigenstates. So even though it's messy, at least we were able to get it. And then if we look at the maximally localized states, those are defined as the expectation value for this modified position being equal to c, and the uncertainty being exactly equal to that minimal localization h bar root beta. We were able to solve for that as this. And again, we can make these states orthogonal by restricting those to the same lattice as before. And the span of these are equal to the span of the eigenstates, and so again, no quasi-position space is needed. We can have a typical position space representation. Looking at the perturbative nature of this approach, if we have some Hamiltonian that is a function of the position and momentum in standard quantum mechanics, we can build a modified Hamiltonian by just substituting in our modified operators. And this gives us a controlled deformation of standard quantum mechanics. And the deviations from standard quantum mechanics we can organize in terms of power of that gut parameter beta. So once we build our modified one, we can break it into pieces, separate out, this is the piece that is just the standard Hamiltonian, here's the linear correction in beta, here's the quadratic correction in beta, and so on. And if desired, we can approximate the higher order corrections away. And so all of the standard tools that we have for perturbation theory are all immediately applicable through this approach. So just a quick key comparison, the phenomenology, the generalized uncertainty principle, the commutator, and the minimal localization are all identical. The core features, the core phenomenology we were looking to find was unchanged. However, the operators are automatically in permission under the standard inner product, whereas KMM, you have to modify that inner product. We have a standard square interval momentum space, whereas KMM's is non-standard. They only have a quasi-position space representation. We have a standard position space representation. Fourier transform isn't unitary under KMM. Ours is preserved. KMM isn't perturbative. It introduces very fundamental changes to the structure of the Hilbert space, whereas this approach is perturbative. The underlying structure is the same, and the quantum gravity effects are now seen as a perturbation. And the key takeaways, again, our approach leaves the phenomenology the same, but the mathematical structure is a lot cleaner and leaves a lot of what we want. It also supports the intuition that a minimal localization should in some way discretize space, even if that doesn't mean a physical discretization of space-time itself. In this case, we found that our discretization was a discretization in our basis. Moving on to the modified quantum harmonic oscillator, we used the KMM gut approach plus the linear term and symmetrized the operator according to the work that I just talked about. So we started with this modified commutator here, which leads to a gut, which I've written here. And this still gives us a minimal localization that is on the order of h bar times that quadratic correction squared. And we take the linear gut term to be on the order of the quadratic gut term squared. Quick review of coherent states in quantum mechanics, standard quantum mechanics, as that's what we use here. The coherent states are eigenfunctions of the lowering operator, which just lowers the energy of the particle by 1. It saturates the Heisenberg uncertainty principle so that the uncertainty in position times uncertainty in momentum it's exactly h bar over 2, the lowest that Heisenberg uncertainty principle allows. And the uncertainty in position is time independent. It's this non-zero value here, but it doesn't vary with time. And the particle moves exactly like a classical particle. It simply oscillates back and forth with time slowly. And then I quick animation here. So the coherent state, like I said, the shape is unchanged, and it simply oscillates back and forth like a classical particle, even though the phase is changing. Tried to get the animation directly embedded in the presentation, but LaTeX was fighting with me. Okay, so to construct our modified quantum harmonic oscillator, we started with this modified position operator, and just like it worked before, we symmetrized the operator to get this here. And then we substituted this modified position operator into the unmodified Hamiltonian for the quantum harmonic oscillator to get our modified Hamiltonian. After doing that and taking the expectation values for x and calculating our uncertainty in position, we get these equations here, which are really messy, and we actually found that looking at the uncertainty in position, it was very difficult mathematically to find any sort of deviations from the standard harmonic oscillator. These don't end up deviating from the standard harmonic oscillator enough that we think it would be able to be measured experimentally, but we did find that these deviations were a bit more substantial, and we hope that the corrections might be able to be measured by experiment. Looking at the leading order corrections, the correction in the linear gut term is on the order of alpha squared times that linear beta, and the correction terms in that quadratic beta are on the order of alpha cubed times that quadratic beta squared, and that alpha is proportional to the amplitude of the harmonic oscillator. So if experimentalists can construct quantum harmonic oscillators that have a very large amplitude, they're oscillating across a very long distance, it will be more feasible for them to measure these corrections. And then atomic system, we were able to place these bounds, so we hope, although the linear term, the corrections, or the ratio of that correction to the standard expectation value for the position is found at the top by 10 alpha, so we are likely not going to be able to measure that through this, but with this term being on the order of 10 to the 15th alpha squared, we think that finding deviations due to that quadratic beta term are likely going to be a bit more feasible. So to summarize, current experiments, they are able to construct quantum harmonic oscillators as well as coherent states, and so we hope that we can find some experimentalists willing to look at this and investigate if they can either measure the gut parameters directly, or if they can at least place some sort of upper bound on what they can be, and help guide future quantum gravity research and future gut work as well. Next, I'll talk about our Lorentz invariance work. I'm not sure what I was going to cut off. So we started looking at Lorentz invariance by starting with a 1D model of our approach. But in this approach, rather than deforming the shape of the commutator, what we did was introduce some sort of cutoff momentum. We did this by taking a modified momentum operator such that it's still approximately p with p is close to 0, but it has a maximum upper bound, which we call p sub m, and that serves as a cutoff. Doing this and deciding that the commutator needs to remain unmodified, we came to the conclusion that our position operator needs to be this, which again is approximately equal to the unmodified operator at low momentum. The same commutator means that they're going to have the same uncertainty principle, and because they have the same uncertainty principle and capital P has an upper bound, we find that the uncertainty in position has a lower bound of h bar over 2 times that cutoff momentum. Again, bottom being cut off, but I can explain what's missing there. The shape of this green line is exactly what the Heisenberg uncertainty principle is, that typical 1 over p, or 1 over delta p, but this red line serves as that cutoff momentum. So everything in orange is what's forbidden by the standard Heisenberg uncertainty principle. Everything in green is what is allowed by the standard Heisenberg uncertainty principle. Then everything in red is what our cutoff momentum is forbidding. So moving on to the 3D construction, we use the 1D construction to motivate and sort of guide our 3D construction. We arrive at these set of operators here. We can't simply substitute p sub j in for p from the 1D model. The modifications are nonlinear, and if we did that, these would not respect rotational symmetry. By making this particular choice, they respect rotational symmetry, and we were able to preserve Lorentz invariance. We proved that these preserve Lorentz invariance by coming up with a modified Lorentz algebra. And then the commutator for this is this equation here, which again, in the low momentum limit, we can see that this will approximate the typical commutator, just I h bar times that delta function. Moving on to some of the phenomenology out of this approach. Case 1, we take a stationary particle that is in a spherically symmetric case, and we find that the minimal uncertainty in position has to be greater than h bar times d minus 1 over 2 times the cutoff momentum, where d is the number of spatial dimensions. Since we live in 3 dimensions, that just becomes h bar over the cutoff momentum, and this implies a minimal uncertainty in volume, which is going to be h bar times the cutoff momentum, or h bar over the cutoff momentum all cubed. And then case 2, if we take that particle to be traveling in just one direction, we find that the minimal uncertainty in position in the direction that it's traveling to be greater than or equal to h bar over 2 times the cutoff momentum, but the uncertainty in the position in the orthogonal directions from where it's traveling has this form here. But due to this form, we see that the minimal localization in those orthogonal directions from its travel are unbounded because the standard momentum is unbounded. However, we do get that minimal localization in the direction it's traveling that we do expect and is bounded. We can also find some non-commutative geometry out of this approach. If we take the commutator between 2 orthogonal position operators, we get this function here, and the operator on the right is just a modified angular momentum operator, which we took into account in our modified Lorentz algebra. In currently studied non-commutative geometry models, they use sort of a similar thing, where they have a non-commutative, position operators aren't commutative, but the commutators are I times some constant matrix. And this is how some people approach quantum gravity starting from the GR side of things. So we've built a sort of connection from this approach to quantum gravity where we're starting with quantum mechanics, other people are starting with GR, and both of us are arriving at some similar phenomenology. This commutator also results in a minimal area, where the area is proportional to the expectation value of the angular momentum. And so this establishes a nice bridge to spin foam models, as this commutator here is a feature of those spin foam models. So to summarize our Lorentz invariance work, We found that minimal localization can emerge from bounded momentum operators and not just modified commutators. We found that a modified Lorentz algebra can be found, which means that GUPs can respect Lorentz symmetry, and so minimal localization to fields doesn't explicitly require a physical discretization of space-time itself. And this approach also induces the minimal cross-sectional area connected to angular momentum, which is a common feature of a lot of other quantum gravity models. So to summarize overall, symmetrizing the operators offers a new approach to GUP models, which seems to fix a lot of the underlying issues with current GUP models, and sort of bring it back to the core motivation of why people started investigating GUP in the first place, where we wanted it to be perturbative on standard quantum mechanics and not change like the overall structure of quantum mechanics itself. The modified quantum harmonic oscillator potentially gives us a way to test these GUP parameters, and if not measure it directly, place some sort of upper bounds to help guide future quantum gravity research. And then we were able to demonstrate that they are compatible with Lorentz invariance, and it also connects to other quantum gravity models. And our work is based mainly on KMM, BOSO, as well as a few papers we've published. Thank you.
Any questions?
I got confused about your what, coherence. Isn't that coherence? You are comparing with the two-way, they had the phase, relative phase is fixed, or you just compare with itself? Got confused. That animation thing you showed.
Oh, the animation. So this is just a coherent state in standard quantum mechanics. The uncertainty position isn't time dependent, the shape of it is fixed. It's oscillating like a classical particle, but the phase is time dependent. This is a single state. This isn't two different states.
Can that still call coherent? I'm not sure.
Yeah, the definition of coherent states is that the position, or the uncertainty position isn't time dependent, and that it just oscillates like a classical particle. The phase can be time dependent.
Oh, I was thinking about diffraction. You talk about the two ways, but they need to maintain the phase information. So that's called coherent.
Well, you're talking about coherence as in like two particles interfering constructively?
Yeah.
Oh no, this is coherent in the sense of we've got a single particle in a square potential. And I'm not sure the history of why that's called a coherent state.
That's a good question. I'm not sure either.
Yeah,
why
I
it's
think
called
my
weird.
guess is that it's called a coherent state because it's the most classical state allowed.
So it's an odd thing. So if you have a simple harmonic oscillator and you take the ground state and you displace it, it does that. Like usually if you take a ground state and displace it, it'll do all kind of crazy stuff. But this basically just bounces back and forth like a classical particle with the same frequency. So it's a really bizarre state.
Yeah, typically if you have any sort of state in a harmonic oscillator, the shape is going to be changing a lot as it oscillates. This is a particular set of, or a particular class of states. The shape just doesn't change with time. It remains, it retains its shape and just bounces back and forth. So it has the most classical behavior that quantum mechanics allows.
Isn't that just an eigenstate? Sorry. Yeah. I got a little bit confused about the
Well, it's an eigenstate of the annihilation operator, the annihilation operator is the position minus the momentum with some constant factors in front.
Any other questions? I have question going back to the first slide. So why do we need to change the uncertainty principle to have quantum or quantum gravity, or is quantum gravity leads to that?
So it's motivated by certain thought experiments. If we consider, say, like we're trying to localize a region of space, and we're trying to localize, say, an electron or something, and we bombard that with photons. Eventually, we've localized it so small that it's going to make a black hole. And if we now repeat the experiment with a new electron, try to localize it even further than we had before, well now, by bombarding it with more photons, we put more energy into it. So it's going to end up making a bigger black hole. Whatever that like minimum amount was, we would consider that like a minimal localization.
So would it be localization of a quantum particle or a particle of the mass? Or how does it relate to gravity? Is
That
there
thought
any
experiment is for a particular particle, but the same thought experiment can be repeated for space-time itself. If we just wanted to localize a region of space-time with photons, we could do that as well.
Any other questions? But let's thank for both our speakers.